To start Unit 1, we will look at arithmetic sequences in the recursive rule. To warm up, we are going to look at a pattern that has different stages. And the question is, if the pattern continues to grow like this, how many dogs will be in stage 15 and how do you know? So in order to figure out this problem, you need to figure out what the pattern is between each stage and continue the pattern until you get to stage 15. So for stage 1, we have 1 dog. Stage 2, we have 3 dogs. Stage 3, we have 5 dogs. Stage 4, we have 7 dogs. Hopefully, you will see the pattern is adding 2 dogs between each stage. So we need to keep adding 2 dogs until we get to that 15th stage. So stage 5 will have 9 dogs. Stage 6 will have 11 dogs. Stage 7 will have 13 dogs. 8 will add 2 more, so that will be 15. 9 will be 17. 10 will be 19. 11 will be 21. 12 will be 23. 13 will be 25. 14, let's add 2 more. 27, and then finally the 15th stage, we add 2 more, that will be 29. So there will be 29 dogs if this pattern continues. And what we're going to be looking at throughout this unit is different ways to answer this question. With what you know now, this would most likely be the approach that you would take. But there are other ways to do it. All right, so we're going to look at a couple of patterns or designs. We've got a mod and Chris. A mod is the top pattern where there's a bunch of different squares. And then Chris kind of has a triangle and a square, but then it looks like a square is being added. So the first thing we're going to want to do is decide how does the design change from stage to stage. And really what that's asking for is, well, what's the pattern? What's happening here? So if we look at a mod's design, you kind of see this X growing. In stage 1, we have a total of 5 squares. And in stage 2, there are a total of 9. So we added 4 to get from stage 1 to stage 2. In stage 3, he added 4 more, these ones on the outside. And so now he has a total of 13. So there is a pattern of adding 4 each time. So our pattern is adding 4. Now for Chris's design, what we're looking at are the number of segments. We're not looking necessarily at the shapes because then it kind of may or may not make sense to some of you. So, they all have a triangle, but then they're adding a square. But let's count the number of segments in each picture. So for stage 1, we have 1, 2, 3, 4, 5, 6. So that's 6 segments. And then we add another square, so that adds 3 more, so that's 9. And then for stage 3, we add another square, which is 3 more, so that is 12. So if we look from 6 to 9 to 12, it is changing by increasing by 3 or adding 3. So our pattern is to add 3. So for question 2, we're looking at the same design, keeping in mind the pattern for a mod is to add 4 every time, and Chris is adding 3. We are trying to figure out the total number for stage 17. So much like the warm-up problem that we did, you're going to need to continue the pattern. So I'm going to try my best to not run out of room here, and maybe I'll try to organize it a little bit. So stage 1, we've got a mod had 5. Stage 2, he had 9. Stage 3, he had 13. And I'm just going to go ahead and kind of do all my stages. Hopefully I can fit it all here. It's going to be close. All right, we'll make it work. All right, so to figure out a mod stage 17, we need to keep adding 4. So we're at 13, add 4, 17, 21, add 4, 25, add 4, 29, add 4, 33, add 4, 37, add 4, 41, 45, 49, add 4, we're at what, 53, 57, and I'm really squeezing this in, 61, 65, add 4, 1 more 9, 69. So in a mod's design, he'd have 69 squares. Okay, so for Chris, he started with 6. Then he added 3, which is 9, then 12, and we're just going to keep adding 3 each time. So 15, 18, 21, 24, 27, 30. Hopefully this one's a little bit easier to add 3, 33, 36, 39, 42, 45, 48, 51, and finally 54. So he's going to have 54 segments in his stage 17. And again, this is not the only way to do these problems, but most of you, this is what you know at this point in time. But we will look at quicker ways to do this. All right, so let's look at some new vocabulary. So we've been looking at these designs and these patterns with Ahmad and Chris, and also that warm up with the number of dogs. These patterns are called sequences, and specifically they're called arithmetic sequences because from each stage, your term is either adding or subtracting a constant number called the common difference. And we use the letter D to represent the common difference typically. So an arithmetic sequence is a sequence where you add or subtract the same number over and over again. So a mod's arithmetic sequence is 5, 9, 13, and then we use the ellipses. A lot of times you guys will say dot, dot, dot. That's called an ellipses, and that's just to show that the pattern continues. Typically, we use 3 numbers to establish a pattern, but it's definitely not wrong if you use 4 or 5 numbers, but you have to have at minimum 3 numbers to show the pattern. The common difference for a mod sequence is 4 because he was adding 4, so I'm just going to put D equals 4. If you just put 4, that would be fine as well. Chris's arithmetic sequence, he started with 6 segments, then he had 9, and he had 12, so the pattern for this one was adding 3, so his common difference is 3. All right, so sequences can be graphed. In order to graph, you're going to look at the stage number versus the actual values in the sequence. In this case, we're looking at a mod's sequence. So in his stage 1, he had 5 squares, and then it was 9, 13, 17, 21, 25, and then 29. And so on. I kept going, but we're just going to graph those because that's all we're going to have room for on this graph. When you're graphing, the stage number will go along the horizontal axis. It's going to act as what you learned last year as X, and the number of shapes will be on the y-axis or the vertical axis. The other thing that's going to be important is to pay attention to scale. It's not always going up by ones on both the x and the y-axis, so you want to make sure you look at that. So if you look at the x-axis, it is increasing by ones, but along the y-axis, if you're looking at it, you might think it's increasing by fours because those are the numbers you see, but there is a little mark in between every one, so that actually means it's increasing by half of that, which would be 2. So this first mark right here is 2. And then 6, this would be 10, 12, 14, 18, 22, 26, and then finally 30 at the top. So when you are graphing, when I go to graph 1 and then 5, 5 doesn't fall exactly at a nice intersection, but it does fall between 4 and 6. So you're going to go up over to 1 to the right, and then you'll go up to 5, and you'll put a point there. For 2, we'll go to 9. 9 falls between 8 and 10. 3 is 13. I'm doing these kind of big because it won't graph them if I do just a little tiny dot, but you should just do like a point, like normal. 4, 17. 5, 21. 6, 25, and then finally the last one that we can fit is 729. So some of the things you have to think about when graphing is, do you connect the points or not? And we're going to talk about it. I'm going to go ahead and introduce you to the word. There's discrete versus continuous. Discrete means that you do not connect the points, and continuous means that you do connect the points. So any sequence is going to be discrete, and that means you're not going to connect the points because there are no values in between. He only has specifically 5, 9, 13, 17, 21, and so on squares in his sequence. He never has 2 squares or 20 squares. So if you connected that, you would be indicating that there are values in between, and there are not. So all sequences will not be connected, or they will be discrete. The other thing that I hope you notice with this graph is that there is a pattern. So if you remember from last year, you hopefully talked about linear functions, which means it forms a line. These points form a line, and that's because of that common difference of 4. Last year, you called that the slope. It's the same thing. So these do form a nice line. Arithmetic sequences should form a line. Okay, so now we're going to look at some more new terminology, and we're going to start with inputs. So input should not be new. Input is what you have always talked about as x, but in a sequence, we typically call the input the index. And I think it's a pretty easy way to remember it because input, index, they both have in the word, and input is x, and index has an x in it. But the index represents the placement of the term or the stage. So like in those examples we were talking about stage 1, stage 2, stage 3, stage 4, that is the index because that is where the term falls within the sequence. If you write all of the inputs together, that is known as the domain. In a sequence, we will use the inputs and set notation to write our domain. And it will be in this specific format. Again, this is called set notation. And the way that's read, I'm going to read the example. It says x such that x equals 1, 2, 3, 4, and so on. So for Ahmad's sequence, his inputs were his stages, which were 1, 2, 3, 4, and so on. I'm just going to use 1, 2, and 3. You could use 4 as well. So to write that as a domain, again, domain uses the inputs or the indexes, which are 1, 2, 3, so on, and it uses x. So x such that x equals 1, 2, 3, and so on. Now these little guys right here are called braces. Set notation always uses braces. The output or y of a sequence is known as the term. The collection of outputs is the range. To write the range of the sequence, we will use the outputs and set notation, and we will use the same format that we did for domain, except for we will use y instead of x, making sure our values are in ascending or least to greatest order. You have to be a little bit careful with that when you are doing range, because sometimes the sequence will decrease, and so they will not be in the right order. They'll be in descending order, so you'll have to kind of flip it around. So if we are looking at a mod's sequence, his numbers again were 5, 9, 13, and so on. So the range would be, using braces, y such that y equals 5, 9, 13, and so on. And again, paying attention to the order, because we were adding 4 every time with that common difference. Our numbers are increasing, so we didn't have to flip the order around. So now we're going to do the domain and range for Chris's sequence. Just as a reminder, his sequence was 6, 9, 12, and so on. So to do the domain, domain is x, and domain represents the index or the position of each number. So with a sequence, 6 is the first term, 9 is the second term, 12 is the third term, and so on. So our domain is going to be x such that x equals 1, 2, 3, and so on. And you're going to see this domain a lot for sequences because their indexes are the first term, the second term, the third term, and so on. For the range, we are looking at the specific terms, and range is y. So again, using set notation, but this time we're going to use y. Y equals 6, 9, 12, and so on, using that ellipses. So as we progress through the unit, we're going to look at some different representations for sequences. So we started with pictures and turning those into numbers, and then we have a few formulas. So the formula that we're going to use today is called the recursive formula. Sometimes they'll use the word rule or form or recursion, but the biggest thing that you need to know is recursive. It is an algebraic model that just helps us make sense of our pattern. You've already, in a way, been using the recursive formula as you've been finding that 15th term or that 17th term. What it does is it just tells you what the first term is, which we can look at the sequence and identify the first term. That is what this A sub 1 represents right here. That means the first term. And so A sub, that means subscript. So that 1 is a little bit lower than that A. So that's important to identify your first term because that's going to tell you where to start. The second part of the recursive formula is the actual pattern. And I know it looks kind of scary, but it's actually not too bad. So A sub n right here just means the nth term, any term in the sequence. So it could be, if it was A sub 50, that would mean the 50th term. Or if it said A sub 102, that'd be the 102nd term. The next part of that is A sub n minus 1. And that just means the previous term. So if you're looking for the 100th term, the previous term is the 99th term. And then the last part is this D, and that is the common difference, what you're adding or what you're potentially subtracting each time. So in words, you're going to give the first term of the sequence, and then to find the term you're looking for, you're going to do the previous term plus the common difference. And if your common difference was negative, it would be minus. So for Ahmad, we're going to start with his first term. For Ahmad, his first term was 5. So I am just going to write A sub 1 equals 5. That means the first term is 5. It's just shorthand notation so that we don't have to write a sentence. The second part is a sub n, which means any term, the nth term of a sequence, is equal to a sub n minus 1, that's the previous term, plus the common difference, and his common difference was 4, so plus 4. The only thing that is going to change when you're writing a recursive rule for an arithmetic sequence is going to be the number you put for a sub 1, because it will vary from sequence to sequence, and the number that you put for d. Again, that common difference can be positive if it's increasing or negative if it's decreasing. So that is the recursive rule for a mod sequence. For Chris, his first term was 6. Okay, so it still says the first term is, now I've changed 5 to 6 because he started with a different number. To find the nth term or any term of the sequence, take the previous term, and his pattern was to add 3. So again, the only thing that changed between Chris and Ahmad's was the actual first term and the common difference. If it's an arithmetic sequence and you're asked to write the recursive rule, recursive formula, it will look like this, but your first term will change and your common difference will change depending on the actual pattern.